spoiler alert, we are going to be doing a chi-squared test, but let's kind of go through it as if we still had to make a decision about which test we had to do. Okay, so remember what I said in my introductory video, which if you haven't seen that, I would recommend as a recap to statistical testing, how you make your decisions, how you do any statistical test, and so on. Okay, so first thing we have to do is use the data to kind of make a decision about which test we're going to do. You might not always be told. So let's look at the data. Let's look quickly at the scenario. We notice that a small snail seems to live only on seaweeds of various kinds. You decide to investigate whether the animals prefer certain kinds of seaweeds by counting numbers of animals on different species of seaweed. You end up with the following data. So what we have is we have got data that is frequency. Okay, so it's mainly numbers of organisms that we're looking at. The other clue is that we're looking at categories. So in this first column, we don't have numbers, we have categories. So that's the main clue that this is a chi-squared. The next thing is that in each category we're looking at frequency, so numbers of organisms, not distances, not heights, weights, or any other continuous variable. We are looking at frequency. Because we've got categories, because we're looking at the frequency of those categories, and we would have an expectation, and when we look at the null hypothesis, this will be more clear. The other thing, and I wouldn't focus on this too much, this is kind of an additional idea, is that we do have an expectation of what we would expect to see given if the organisms didn't have a preference, or if they did have a preference, we kind of know what we would expect to see. So if they didn't have a preference, then the numbers of these animals on each kind of seaweed right here, they would be all the same. Okay, but if they do prefer a certain type of seaweed, then the numbers we would expect to be different. So that's the other thing that tells you that this is an observed versus expected kind of situation, and therefore that's how we're going to approach it with a chi-squared test. So first step, not going to mess this up this time. First step, we are going to make a null hypothesis. And in this case, the null hypothesis, remember, is the opposite of your experimental hypothesis. Now, if I'm a biologist and I know some stuff about species, adaptation, niche, etc., I would, based on that, think that, well, animals have a certain set of adaptations. They would have a certain preference of seaweed because their adaptations would mean that they're more adapted to one type of seaweed than others. Okay, so that's my experimental hypothesis. My null hypothesis would be the opposite of that. My null hypothesis, because I'm going into this as an unbiased scientist, my null hypothesis would state that there is no preference of the animals for different types of seaweed. Okay, and therefore there will be no difference between the observed and expected values. Something along those lines. Okay, that's my null hypothesis. 2 is to actually then do the test. Okay, so let's just remind ourselves about what the chi-squared equation is, and then we'll look back at the data and we'll start. So the chi-squared equation is the sum of the observed frequency minus the expected frequency, essentially the difference between the observed and the expected, each difference is squared, and once each difference is squared, it is divided by the expected value, and then each of those is added together, and that is going to give us the chi-squared test statistic. Okay, so let's proceed with that. Okay, now the main challenge with the chi-squared, once you've decided to do the chi-squared test, the main challenge is you've got your observed values. So your observed values is essentially your original data. Okay, so don't forget that these were the observations. This is what the data is. One of the challenges of the chi-squared test is to work out what the expected frequencies should be. And I would say, in order to work out what the expected frequencies are, pay close attention to your null hypothesis. Okay, so the null hypothesis states that there is no preference of the animals for the different types of seaweed. So in the case that the animals had no preference, we would expect that the animals would be equally distributed over the different types of, or across the different types of seaweed. Okay, and this is where essentially, let's just write this down. Expected frequencies, or expected frequencies, are based on the null hypothesis. The null hypothesis usually states that there is no difference or no preference, okay, or nothing unusual, okay, nothing unusual. Okay, now sometimes this is not true for every single chi-squared test. This is important. Sometimes you have an expected frequency that is unequal, and you have to go with that. In this case, we don't have necessarily an expected frequency of each category, but we do expect that there's no preference. Okay, so be careful about that. If you had a bag of Skittles and you knew that you had double the amount of red Skittles versus blue Skittles in the bag, you would expect that the number of Skittles that you pulled out of each color out of the bag at random, you would expect that there were twice as many that you pulled out of one color versus the other color. So because you know that going into it, you would expect that the distribution was unequal, and you even knew that you would expect double the amount of one color versus the other color. So it's not always the case that it's equal. Base it on your null hypothesis. Okay, so in this case there's no difference, and so I would expect the frequencies to be equal on all the categories of seaweed. Okay, and now the way we do that is we look at the total or numbers of the animals that there are. In this case is 100 animals all together, so we add all these numbers up and we get to 100, and then we say, right, then if they were equally distributed, it would be 100 divided by the number of categories that there are. In this case there's 5 categories, so the expected frequency would be the total frequency, let's say, divided by the number of categories, and in this case that equals 100 divided by 5, which would give me 20 in each category. So if it was the case that there was no preference of the animals for the different types of seaweed, I would expect there to be 20 of each, or the frequency of the animals on each of the seaweeds to be 20. Okay, so let's proceed now. We have an idea of what our expected frequencies will be. We know what our observed frequencies are, and we'll proceed now. And remember, with the chi-squared, that's essentially all you need. Once you already had your observed to start with, Now you know what your expected frequencies are. We can proceed with the calculation. So now that's the equation. And however, what we can't do is simply put our observed and expected values directly into that equation because it's not that straightforward. Remember, we need to repeat this part for each of our data points, data sets. So we have type of seaweed, we're going to have the observed values here, we're going to have the expected values, and then for each of those we will have to calculate the observed minus the expected. Then for each of those values we'll have to do that value squared. Okay, and then after we've squared each of those values, we'll have to divide them by the expected. So O minus E squared divided by expected. And once we've got each of these values, at that point we are going to add them all up, and that should give us essentially what the chi-squared value is going to be. Okay, so let's begin. So we've got our data. So we've got 40, 45, 38, 10, 5, and 2. That's our observed data. That's the original data that we started with. And we said that, well, if there was no preference of each of the different on each of the different types of seaweed, in that case we would expect 20, equal distribution of 20 in the expected. Then once we've got the observed and expected, we then do the subtraction. So 45 minus 20 should give us 25. 38 minus 20 should give us 18. The difference between 10 and 20, or 10 minus 20, is going to be minus 10. Okay, let's put the minus 10 there. But don't worry about this. This is about differences, really. So you can put minus 10 down, technically that's correct. But we are going to square this. We're going to square this value, so you should end up with a positive value in either case. So really, having that minus sign there or not should make no difference. The difference between 5 and 20 is 15. The difference between 2 and 20 is 18. Okay, so really that negative sign shouldn't affect things because we're going to square these values, and whenever you square a value, whether it's negative or positive, the squared value is always positive. Okay, so let's begin with, so now we are here and we will be squaring each of our differences. So 25 squared is 625. 18 squared is 324. Just for fun, we'll put in minus 10. Okay, and square 10, and guess what? It is 100. Okay, so you can ignore that negative sign. 15 squared is 225. 18 squared is 324 again. Now we've got that. Now for each one we have to divide each of those values by the expected value, and we're nearly there. Okay, so 625 divided by 20 gives me 31.25. 324 divided by 20 equals 16.2. 100 divided by 20 is 5. 225 divided by 20 equals 11.25. And 324 divided by 20 equals 16.2. And now we just have to do this last step, which is to add all those values up. Okay, so let's do that. 31.25 plus 16.2 plus 5 plus 11.25 plus 16.2 equals 79.5. 79.9. So that, ladies and gents, is our chi-squared value. Chi-squared is equal to, in this case, 79.9. What does that number mean? Absolutely nothing until we've done the next step, okay, which is to calculate the critical value or determine the critical value. Okay, so let's remind ourselves what we did. We did our null hypothesis, we've made that. We've calculated our test statistic. In this case, it's chi-squared. So our test statistic is equal to chi-squared is equal to 79.9. And now what we will have to do is work out the degrees of freedom to calculate, to get our critical value. All right, so critical value we must get from the table, from the critical value table. But remember, we go across to 5% significance level, we need to go down the degrees of freedom. So before we can find that critical value, we must get our degrees of freedom because we don't know how far down the table to look. Now for a chi-squared test, the degrees of freedom is equal to the number of categories from your original data, the number of categories minus 1. So we had, let's check, 1, 2, 3, 4, 5 categories. So our degrees of freedom is 5 minus 1, which is equal to 4. Okay, so we've worked out our degrees of freedom, and now we're going to refer to the chi-squared critical value tables to determine what the critical value is based on the type of test that we are doing. So remember, we're looking for across, as we go across, we're looking at a 5% chance of error or a 95% kind of confidence level, okay, or a significance level of 95% or a chance of error of 5%. So that's the 5% right there going across, and down we want to look for our degrees of freedom, which is 4 right here. So the value, our critical value that we're looking for is 9.4. 9.488. Our chi-squared value was 79.9, so much higher than that. But to talk about that would be to go into step 4. Now we don't want to start step 4 prematurely, do we, guys? All right, so let's do that. Step 4, now we make the conclusion, now we make the comparison. Okay, so step 4 is all about saying that yes, in this case the chi-squared value of 79.9 is greater than the critical value at the 5% significance level, or 5%, yeah, 5% significance level. Therefore, and that's our first part, B, therefore, what does this actually mean? Well, it means that we have to reject the null hypothesis and conclude that there is a preference. Remember, we bring it back to the context of the question. Conclude that there is a preference of the animals for particular species of seaweed. Okay, the distribution is not equal, right? However, we accept that there is a 5% probability of being in error about this conclusion. Okay, and that's chi-squared. If you've got any questions, any further questions, do leave a message for me. If I've made a critical error at any stage, do let me know as soon as possible so I can maybe rectify it. But yeah, thanks for watching. I hope this has been useful. The next video will be on the Spearman rank correlation coefficient.